So yeah, welcome to our popular science seminar. I'm the presenter today. I'm going to talk about Neuro Evolution and Machines that learn by themselves. And I mean, yes, in the popular science seminar, we present topics that are interesting to each other, to sort of get to know each other across the different institutes and to explore future options, collaborations, ideas. That's the idea. So yeah, let me move stuff around. Sorry. Okay, so yeah, I'm going to talk about Neuro Evolution and machines that learn by themselves. So when I say machines that learn by themselves or artificial intelligence, I actually do talk about these machines, right? This is all pictures from Hollywood from somewhere between the 60s, 70s, 80s, 90s that show robots that do fancy stuff. That's how Hollywood depicts them. And this is also what I think about when I say AI. And we can talk forever about the question what actually intelligence is. And we can make this discussion only worse by also arguing about what consciousness is. So let's not try to really define this, but let's try to think about important properties that intelligent systems have to have. And I think one of the most important ones is that these machines can learn by themselves. Not only learn, that would mean that I tell them something that I can repeat what I told them. No, that they actually explore the environment by themselves and then exploit the environment and learn something about the environment autonomously. You want them to sort of do things by themselves and be able to improve their capabilities autonomously. So being able to learn by themselves is an important property of intelligence. And that's kind of what I'm interested in trying to research. Now, when we look at the current technologies that we have in artificial intelligence that go in this direction, we have deep learning, we have reinforcement learning, and we have genetic algorithms that optimize the properties of systems. And I'm really interested, or I use mostly genetic algorithms. And when we apply genetic algorithms on computational systems that are supposed to do cognitively interesting tasks or that should have cognition, we talk about neuroevolution. So neuroevolution is a subset of artificial intelligence using genetic algorithms on those AI or artificial intelligence systems. Okay, let's take a look at these three systems and let's try to find out what they specifically do and how they contribute to the current cloud or world of artificial intelligence systems. We start with deep learning. And in deep learning, we have artificial neural networks. Artificial neural networks have an input layer on the left here and an output layer on the right, and then lots and lots and lots of layers between them, which are called hidden layers. And typically all nodes of a hidden layer are connected to all nodes of the next hidden layer and so forth. And when we want to train these neural networks, we present them with inputs. Let's, for our sake, here say we would like to have this neural network to be able to distinguish cats from dogs. In this case, cat silhouettes from dog silhouettes. So what I do is I take an image from a cat and I run this thing through the network and it spits out two numbers in our case. Okay, 0, 1 and 0, 2. What we want this network to do is to be able to distinguish between cats and dog images, and we code in such a way that it recognizes a cat when it says 1, 0, and it recognizes a dog when it says 0, 1. That's what we would like it to train to do. And what it does is it produces these two values, which are different from the output that we expect. However, we can compute the error between those two numbers, and then we use what's called backpropagation and pretty much massage this error back over the network in such a way that when I next time show the image again, the error that I have is smaller and smaller and smaller and smaller until this network actually recognizes cats and dogs appropriately. And I do this over lots and lots of input images, and I do this repetitively, and there are lots of optimization in there, but generally speaking, this is how neural networks work. So you immediately provide an objectively correct answer. So you let this forward pass go and you compare this with the answer you expect immediately. And the answer is also objectively correct. You identify those images, the training set in the first place. And the second thing is you compute an exact error. You identify exactly what is wrong, and you also tell this to the network to correct. And then you, massage the weights according to minimize the error. This is a rather fancy mathematical operation that does this backpropagation, but nevertheless, you change those weights in order to produce the outputs that you expect. And it turns out that a very, very large degree or large part of of artificial intelligence systems that we have right now are based on exactly this technology. So these systems already make a very, very big impact on our lives, and they are trained in this rather specific fashion. Okay. Let's go to reinforcement learning, because that's actually a little bit different in that generally speaking, we have delayed rewards. So what we want is we want to train this little card to go up to the right side where the little yellow flagpole is. When it reaches this yellow flagpole, then we give it rewards and say this was good. However, this task, this specific one, is designed in such a way that you cannot just drive up. You have to drive to the left, get a little bit more momentum, and then you can actually go to the top right side. So it's not a direct path. You cannot just go there. You have to do other things before you reach the reward. Now, in order to train this, you have to define what is called a policy. The policy actually takes the input, which is the locations of the card and where it currently is, and then this policy actually predicts reward or outcomes of actions. In our case, when we start with a policy, the policy is really uniform distributed or equal probabilities on all actions. For example, when you go to the left and you're in location 0, well, there's a reward of 50 or 0.5 for going left and a reward of 0.5 for going right. So you don't know which one to do. You just randomly choose between them. So when you train this and you start training this, what you do is you take your random policy and just let this card running around. And at some point, actually, this card, more or less by chance, will whoop up to the goal, and then you can reward it. So you record all of these actions that lead up to this moment, reaching the point where you can tell the reward, because reaching the target is a reward of 1, and not reaching it is a reward of 0 in this particular case. Now, this path that the cartwheel here, or the cart actually took, has a couple of properties. For example, all the actions that are completely meaningless, I just move back and right, back and forth, well, they come with the same frequency. You go as many times to the right as you go to the left without moving the cart. But overall, since this path actually led to the goal, this path contains more actions that are meaningful, that lead to the solutions, than those that are meaningless. Which means if you now positively reinforce, that's why it's positively reinforce, all those rewards that are leading to the goal, you on average improve the policy over its predecessor. And you do this a couple of times over and over and over. And at some point you arrive at a policy that more or less perfectly predicts the rewards and then allows these predicted rewards, or following these predicted rewards, to actually reach the goal. So in a perfect trained policy, it would actually go to the left and then go to the right, because that's how it leads to success. In order for this to work, as you see, we do a couple of things differently than deep learning. Well, first of all, it deals with delayed rewards. This is something that deep learning doesn't do, right? Deep learning immediate rewards, here delayed rewards. This is a big advantage over that other method. The second one is you do not need to compute the exact error. Right? That's something that deep learning again does. You don't need to provide the exact things that are wrong. You just pretty much positively reinforce those things that were good, and then the quotation mark sorts itself out. It struggles with what's called hidden states. So you can do reinforcement learning on things that have a defined state. On things that have a hidden state, something that's unknown, well, that doesn't really work. If, for example, the card has to know that it picked up a key before it can go to the goal, it wouldn't be able to do that, because the key has to be remembered, and that would be a hidden state, and you can't do that. For most applications, it's actually not that difficult. We can formulate many tasks in such a way that they solve the hidden task, hidden state problem. Okay, let's go to genetic algorithms. And for genetic algorithms, we look at the same problem again, this little card problem. But keep in mind that we can apply genetic algorithms to lots and lots of other technologies and other problems. But for our sake, let's try to solve this problem with a genetic algorithm. What we do is, well, we can generate lots and lots of policies, different ones, randomly generated at the beginning. In fact, we create a population of policies. And the little gray tones in there mean that they're all a little bit different. Since all of these policies are a little bit different, we can compute how well they perform. And for that, we need what's called a fitness function or objective function. And there are different ways of doing this. I just here, for this example, say that the time remaining after reaching the flag is the performance of the agent. So if you give the card or the agent 1 minute to wiggle around, and it reaches the end or reaches the flagpole after a couple of seconds, and the remaining time is its performance, which means the earlier the card reaches the flagpole, the better it is. Well, when you generate lots and lots of policies, chances are most of them will be actually terrible and not reach the goal. And I just, for illustration purposes, said there's one policy that's really good that reaches the goal after 20 seconds, so that 40 seconds are left. one of them reaches the goal after 50 seconds or 10 seconds are left. And then down there, we have the last one that is really bad, but it still reaches the goal 5 seconds before the time is over, and the rest now. Now, different ways of creating the next population, but the most prominent one is that you create copies of the solution proportional to their performance, which means the solution that is the best will have more offspring in the next generation than other solutions that are worse. And here, for example, we do not copy even solutions that have 0 performance. So we create a new population. This is sort of the next column, but you see the little orange flags in there. It means every time we copy a solution, there's a chance that the solution is actually changed a little bit. We change the rewards in this policy table, for example, with the idea that maybe we find a policy that's a little bit better than its ancestor. It turns out that most changes that we're doing are actually worse than what we have. So the fewest changes we do actually improve the performance, particularly if the problem is difficult. Anyways, when we do this over many, many, many generations, what we arrive at is a policy that actually drives the car up there, but trial and error. Now, the big difference to the other two methods is that the rewards really comes at the end, right? We just let the car run, and once it finishes, that's when we reward it because it goes in the next generation. So you cannot, quotation mark, learn from the fitness function during your lifetime, because the fitness function in this particular case is applied after lifetime. It's a post hoc thing, which means whatever the card or the policy has to find out, it has to do this autonomously by itself, just so that in the end it receives the reward. The rewards are fuzzy, right? I mean, I just said a couple of minutes and you're faster, but you can define lots and lots of different ways of fitness functions. So that makes the reward structure rather interesting and rather amenable to all the problems that you have. But it also not necessarily rewards particular actions. It rewards, quotation mark, the holistic experience of your life, so to speak. You have to do overall good. And now, the last one that also makes it different to reinforcement learning is the fact that genetic algorithms or evolution is what's called substrate independent. As long as I can create a copy of something and modify a little bit and measure its performance, I can apply a genetic algorithm and improve this set of solutions towards my objective function. Reinforcement learning is necessarily dependent on a policy, and deep learning typically is dependent on a neural network. Whereas the genetic algorithm can be applied on arbitrary structures. So it expands this knowledge, or this cloud of tools a little bit more. So let's compare when reward or reinforcement or information about the environment happens. As I said, in deep learning, every time, all the time, accurately, immediately. Reinforcement, in the beginning, reinforcement or positive reinforcement is rare because performance is poor, but after performance becomes better and better and better, you get more and more rewards and so forth. And in the genetic algorithm, reward is really after your lifetime and not specific to the actions that you did. Now, I said I'm interested in agents or machines that can learn during their lifetime by themselves, which actually precludes me using deep learning and reinforcement learning. But it also imposes a rather interesting problem, and that is, how do I formulate a fitness function in such a way that my agents do learn during their lifetime? The interesting thing is we have precedents for that. Because you and I are evolved machines, we can learn during our lifetime, and we were selected by some unknown objective function. So we have precedent that this works. And let's take a look at how we humans evolved this. So this is the phylogeny of human evolution from 10 million years ago. You see that monkeys actually sort of branch off quite early, 6 million years ago. And we are looking at this last branch on the left side after 4 million generations. You see that on the top left, I hope you see my mouse cursor, there's Homo sapiens, that's where we are. So we are looking at this last trajectory. And around this time, we find laterally footprints. And I have to say, I think laterally footprints, in my opinion at least, are the coolest fossils we have. They tell an amazing story and they're very, very revealing. The laterally footprints are about 3.7 million years old, have been found in Tanzania. And they actually come from Australopithecus afarensis, which is one of our ancestors. When you remember Lucy, the Lucy fossil, the little 1 meter high hominid, she was also Australopithecus afarensis, and her fossil is about 4 million years old. So these footprints are from Australopithecus afarensis, as far as we can tell. It's always a little bit tricky with paleontology, but let's just assume that for a moment. The footprints actually do not have knuckle prints. monkeys and gorillas and so forth run on their knuckles, on their arms, these footprints don't have those knuckle prints, which means that these organisms that ran there were upright. That's super important because now you have your hands free while you're walking, and you can do lots and lots of things with this. You can point, you can wave, you can use your hands for tools, lots and lots of things. But more importantly, you can hold stuff. I'll get to that in a second. The other thing that we observe is that there are three individuals, not just one set of footprints, it's three sets of footprints, which means that this group actually lives in at least some small social group. It's not an individual, it's not a couple, it's more than two. And also, it's not 50 footprints that we find. So we kind of assume that the social groups we lived in are actually rather small. And this is something that we also observe over whole human evolution. And we also know that one of them walks asymmetric. One of the individuals actually puts more weight on the right foot, and with forensic analysis and so forth, we kind of assume that this individual was carrying a baby. And I think this is a really beautiful image that at the sort of dawn of human civilization, we have them actually carrying a baby, all groups together in the sunset. And they work so closely together that their arms cannot just swing freely in their movement pattern, which means we also assume that they actually held hands. At least two of them did this. I think it's a perfect romantic image about this past. And it says so much about humans, how we lived and how our evolutionary conditions were. But let's take care of living in a social group, because living in a social group allows us to do something very specific, and that is division of labor. The moment we live in a social group and we can divide labor, we can actually do much more than if we wouldn't do that, if we would live alone. However, it requires us to actually make decisions about how the labor is to be divided. And it turns out that, for example, social insects already solved this problem. Ants use genetics to solve this problem. You have the genetics that define whether or not the individuals are queens and males. If they're haploid, doesn't really matter. You create a normal-sized worker, and if you do something else, you create soldiers. The trick is that you have a very large group, and you have a deterministic process, in this case genetics, that predetermines their role in their society. Very inflexible. It also doesn't matter because there are lots and lots of individuals in there. Now, a little bit more adaptive way is what honeybees do. Honeybees actually use their age to define what role in the hierarchy they are playing. The rule of thumb for honeybees is that the younger they are, the closer they are to the queen, and the older they are, the further away they are. So in the beginning, they actually take care of the young, distribute honey, receive pollen from the workers. And at some point, when they're actually, I think, over 30 days old, they actually start foraging outside and fly and collect honey. And once they're arriving sort of senescence for honeybees, like really not capable of collecting honey anymore, that's when they defend the hive, because they're kind of expendable. If they die, there's no other function that will not be carried out. So you can use them as dependable, expendable soldiers, so to speak. Tough life, but that's what honeybees do. They use age to actually control the division of labor. When we go up what we humans perceive as sort of the complexity hierarchy, we get to more and more complicated organisms. Well, the ability to divide labor becomes more sophisticated. If you look at a wolf pack, for example, they define the roles of the division of labors depending on what we call conditional predisposition. Individuals that are really smart and have leadership abilities, quotation mark, actually become alpha males and lead the group. Those that are really strong defend the group and so forth. So we get to the point where we can dynamically adapt to the situation and sort of choose roles depending on condition and predisposition. Now, what about humans when we get to humans? And it turns out that we as a group of humans, or in any group, are extremely capable of dividing labor and making decisions about this on the fly instantaneously. We can do this amazingly well. Well, because we have to be able to replace each other. If you think about one of these early ancestral groups, well, if one of them dies, and of course early hominids die a lot, you have to be able to replace that function. If this is the person that carries the water, you have to replace the water carrier. If this person is the one that collects the mushrooms, or is the one that hunts saber-toothed tigers, this is how we imagine this, but I mean, they did lots and lots of other stuff. You have to replace those roles. And you have to do this depending on the situation. It's not clear that always the oldest one dies, right? In the accidents and so forth. So we are in a situation we have to take advantage of dividing the labor given the current situation. Now, instinctual behavior is insufficient to solve this. You can do a lot with instinctual behavior, but these dynamic changes and also our sort of requirement to communicate and so forth cannot be encoded in the genome anymore. Not because the genome doesn't necessarily have enough space, but we don't know how to actually store information about language in the genome. The ability to speak and the ability to learn a language, that's for sure encoded in our genome, but not the language itself. We actually learn something during our lifetime in order to sort of live up to the potential that our genes give us. And in order to actually satisfy all of this, we have to be able to learn during our lifetime. So the proof that we can do this is actually like 2 million years later than the lateral leaf fossils. During these 2 million years, humans actually developed the ability to actually do learn by themselves from others. Because until this point, 1.7 million years ago, we find stone axes, but we find stone axes very primitively made, and we kind of assume that they are tools that humans build instinctively. But 1.75 million years ago, some human actually apparently invented a way to carve a new stone axe that was really good. And we have a rapid expanse of these stone tools across the continent of Africa. Pretty much like a meme spreading through the internet, we have suddenly stone axes spreading through the human population, much faster than the genetics would allow that. Which means humans at that time were already capable to at least some degree of social learning. The environment they lived in, the small social groups and their requirements, actually allowed them to develop this ability so that they could, in this very moment, learn from others how to make stone axes. And that's really the onset of what we call social evolution. That is actually responsible for all the funny stuff around us. Okay, so if we think about the evolution of learning, well, evolution did not specifically select for learning, right? Evolution rewards organisms' ability to explore and to exploit their niche. And it just so happens that learning, and specifically social learning, is an incredibly useful thing when you're a hominid and live in a small group, which means these are the conditions under which evolution can evolve. And it just so happens that it did in this particular case. So we kind of have a rough idea where it's coming from and how it happened. Making actual experiments about it is extremely difficult and evidence is really sparse. But I have to say, I think this is a really good story that explains how we arrived at this ability. So if we want to use evolution to create machines that learn, well, we have to replicate this idea somehow. Okay, so if you want to evolve learning, you have lots of problems, but the three most important problems you're facing, or that I'm facing, are the following. Neural networks, which is sort of this standard technology to do that, to do these things, well, they're not plastic, adaptive, malleable, or evolvable for that case. They are really only good at receiving backpropagation. I mean, they're made to do this, and they're really good in this function, and that leads to lots of cool applications, but they're not really evolvable. So we have to sort of solve this somehow, develop evolvable neural networks. The second problem is that we don't know which environment allowed learning to evolve in the first place. I mean, we have a good hunch and I can tell a nice story and we can imagine that, but you have to actually recreate these conditions. I'm going to show you a couple of examples, but you need to find a function to evolve learning, which is less easy than you think it is. And then lastly, if you want to show that your systems actually do learn and actually have an algorithm that allows them to adapt and to store information, well, you have to understand how information propagates through the systems and where they actually do save what they've learned. You need to understand the systems that you create, right? Otherwise, you don't know what you did. You just recreate the phenomenon, but don't know whether or not it actually does what you think it does. So we have to figure out where memory is stored. And I say memory as a sort of loose analogy to the stuff you learned, okay? So we need to sort of solve these three cases. Well, develop evolvable neural networks. This is not super easy, but we approach it in this way. This is an artificial neural network. I showed you this image before. You have an input layer, you have an output layer, and you have structured stuff that you predefine lots and lots of weights in there. So we created something that's called a Markov brain. A Markov brain, in order to be compatible with artificial neural network technology, has an input layer, arbitrarily large, has an output layer, arbitrarily large, and therefore it can actually replace a neural network. However, the structure, meaning all the hidden nodes, they're evolvable. They're not predefined where they are, what they do, and what they contain. They can sort of be freely accessed, and they're accessed by what we call logic gates or computational units. These computational units actually take information, perform a computation, and put that into a hidden node. And then the hidden node actually can be read by the next computational unit that performs a computation, writes this into an output node or a next hit node, and so forth and so forth and so forth. Okay. The computational units that we use are in most cases either probabilistic or deterministic logic gates. Sometimes they're mathematical operators, but they are also, or we will also allow them to actually just be aggregation and transfer functions like neural networks. So it turns out that Markov brains, the way we set them up, is a superset of most of our computational tools that we have, with the advantage that we can actually evolve not only their structure and topology, but also the individual functions and how they work together. Okay, so from that point, we have a very, very evolvable neural network structure. We can discuss how evolvable it really is, but it is adaptable. Now, and lots and lots of research goes into this, but let's go to the next one. Let's try to think about the fitness function to evolve learning. How do we approach that? Let me show you a simple task that we can try to solve using or evolving a neural network that controls an agent. Our little agent here is an orange triangle, and the agent always looks down on its feet, and it can be on an empty spot, it can sit on a circle, it can sit on a star, it can sit on a diamond, or it can sit in the purple stuff. And the purple stuff is poison. So it's not killing it immediately, but it's bad. You shouldn't be too long in the purple stuff in the poison. And what we want this agent to do is collect all the little circles. Because it can only look down, if it would take a step forward, it could actually step into the poison. However, we pave the path in such a way that whenever there's a left turn, there's a little star, and whenever there's a right turn in the path, there is a diamond. So following this path, they can collect the dots perfectly fine. And well, today, as I said, stars means left and diamonds mean right. So without any further ado, if you evolve this, they can solve the task super quickly. However, when I said today, it means every time we put an agent into the environment, we randomize what the star means. Half of the time star means left, half of the time star means right. And correspondingly, if star means left, diamond means right, and so forth. So that's why it's sort of an associative memory test. You have to associate the symbol that you're seeing with a particular action. Well, if you evolve this, we can evolve them really quickly to do this problem, except that it becomes tricky to say whether or not they learn something, because the solution that they arrive at can best be described with 2 brains and a switch. We did this in different substrate, different models, and it's always kind of the same strategy. They actually run into the first symbol, either take a right step or take the wrong step, and then after that they know whether or not they know what the signal means. And if they know what the signal means, they run one particular program. This one particular program in this case means stars mean left. If they are wrong, they sort of turn that strategy off and turn on the other strategy. They sort of use their other brain. And the other brain says star means right, diamonds means left. And that's it. They kind of exploited the fact that you can sort of offload this problem into a single solution, sort of the 2 brain switch solution. It's entirely possible that easy tasks in the beginning have evolved to be like that, but that's not the adaptive, nice memory learning function that we want. Nevertheless, it's a step towards memory that is acquired during the lifetime. Disappointing, but still it does roughly what we do. So, and also, how does the brain store the symbol? Where is that symbol in the brain? It's really difficult. In this case, it's in the switch in the beginning, and then after that, you're sort of down in the flow chart doing one thing or the other. Okay, let's try to use a much more complicated task. And this complicated task, again, is sort of a navigation task because they're easy to code. You have an agent somewhere in the environment, and you have a star. That's where you have to get. And again, the agent can only look down, but we make it really easy for the agent to actually find the star because the tiles that it's standing on are marked with arrows. And the arrows point always to the shortest path to the star. So you just need to read the tiles that you're standing on and then move accordingly. Except that move accordingly, meaning turning left, turning right, moving forward, standing still, is encoded with a button. And this button sometimes, the triangle button, for example, sometimes means move forward, the square means move left, the X means move backward, and the circle means right. Well, if that would be how buttons map to functions, that would be perfectly fine. You can learn this immediately. Yeah, but every time the agent is born, we randomize what the buttons mean. And it's actually quite funny. If you play this yourself, it is hellishly difficult because like, what was the button again? And you only see what's below you. Difficult as hell. And the cool thing is that there are so many button combinations. I think it's 24 possible combinations of buttons. Maybe it's 23. This is way too complicated as what we call hidden state to learn by backpropagation or by deep learning. You can't. So let's evolve Markov brains. They should be able to solve this problem. And it turns out that Markov brains, the way they are at that particular moment, actually struggle enormously with this. We get some that do okay on the task, but way less, way apart from what we would call perfect performance. Okay, so what is missing here? Right? Well, I showed you what a Markov brain is, and a Markov brain is defined by a genome in the beginning, and then it's fixed. And this is not how you and I learn. We're not learning with a fixed brain. Our brain has the capability of changing during its lifetime. We actually rewire a lot. This is not what we did. We actually allowed dynamically or adaptive gates or computational units. In this particular case, we introduced a new unit, and this unit is what we call a feedback gate. A feedback gate works a little bit like Q-learning or reinforcement learning, in that it actually stores what it does, and when it gets a positive green signal, well, it reinforces the computations that it did. It pretty much assumes that what it did before was good and leading to the goal. And that's why it tries to do those computations again next time it appears this. If it gets negative feedback, it sort of downregulates this and tries to not do those things again because they were bad ideas. Important, the feedback that this gate receives is not objective feedback from the experimenter. That wouldn't work because in an evolutionary algorithm, you get feedback once you're dead. So that doesn't work. But it receives feedback from the brain itself. The brain has to develop the ability to recognize what's good and what's bad in the brain, in the environment, what its action, and then uses this to actually reinforce this. And once we use this type of structure, where we have adaptive brains that can change during their lifetime, we can solve this task actually quite nicely. There's one problem that we're still sort of chewing on, and that is we do not change how things are connected. Right? As I said, neurons actually change how they are connected. Synapses are made and disconnected all the time. And that's a very, very important part of learning. We only change what the quotation mark neurons do and how they do computations, not how they're connected. That's kind of really an open question, quite interesting to study. But at least we get into the direction of having more adaptive brains. Okay, last problem, figure out where memory is stored. So when we evolve brains, that's how they look, right? The red circled black nodes on the top are inputs, the green ones are outputs, and the blue ones are hidden states. And every time there's a gate connecting one node with the other, I drew a circle. Yeah, that looks pretty messy, and it's also incredibly hard to understand. If you try to write down what this brain does in a narrative, and we tried this a couple of times to just make sure that these things work the way they are and that's explainable, well, you need like 3 people that argue with each other for like a week or so, and then you arrive at sort of a narrative about what they do. And yeah, we can actually evolve these brains faster than we can analyze them. So that's really a bad approach to this. So we need some kind of automatic procedure that tells us what's going on. And particularly in our case, where the memory is stored, because we want to find out how they memorize something and also how they use these memories. So we developed this information theoretic measure, R as in representation, and R quantifies how much a brain knows about its environment. And I know information theory is not really for everybody, but M, that's the circle on the top right, these are the brain states that you have. And E, that's the circle on the top left, that's the environmental states. The surface between those two, the environmental states and the mental states, that is the information that the brain, the mental states, have about the environment. However, we have to subtract R. We have to subtract S. That's the state of the senses. Because when you see me, you know that I'm wearing a red shirt. That doesn't mean that you know internally that I'm wearing a red shirt. You have to look away for me to test whether or not you know that I'm wearing a red shirt or not. And this subtracting information is recapitulating this. That means that the amount of representation that you have about the environment is defined by the amount of information shared between environment and mental states, given the sensor states. And this is the complicated way of writing this in information theory. So that allows us to quantify how much information a system has. But we can do a little bit more. We can use this in order to find out what component knows how much, what component of the brain knows how much about what environmental concept. So I just drew 4 environmental concepts. They are A, B, C, D. Doesn't really matter what they are. We can apply this measure and ask how much does node 5 know about R? How much does node 5 know about C? And so forth. In a systematic fashion, we find out how much every node knows about every concept. And if we push this to the extreme, we find that memory is sparsely distributed. So, and this is actually not only true for Markov brains, this is also true for humans. If you have a particular memory, let's say your grandmother, then not every neuron in your brain has the information about your grandmother. And it's also not just one neuron. I mean, there's something called grandmother neuron. This hypothesis has been debunked. You have lots of neurons that specify or fire when you think about your grandmother. And at the same time, you have lots and lots of neurons that fire when you think about your grandfather. Interestingly, there's an overlap between these two concepts. And that means that your memories are also sparsely, because not everything, and they're also distributed because they're kind of sharing other information. And this is exactly what we evolve when we have Markov brains. We get sparsely distributed representations. Curiously, when you repeat the whole procedure on artificial neural networks, and in artificial neural networks, every node in the layers connects to every other node in the layer above and connects to every other node in the layer below, we find that memories are not sparsely distributed. In fact, in neural networks, information is what we call smeared. Information is overlapping and distributed over the entire network. It's like every node is important to understand this. And it's not really clear why this is important for a function of a network. I mean, you get functional neural networks regardless of smearing, that's independent. But it seems as if the backpropagation algorithm or the backpropagation algorithm, because it finds out the contribution of every node to every node, it actually reinforces all those nodes at the same time. Sorry. Oops. Finds out the information from all nodes to all nodes. And that's why information is smeared. Now, that's rather interesting because neural networks have lots and lots of really awkward shortcomings. For example, they struggle to generalize. They have what's called catastrophic forgetting, which means if you train them on a new task, they forget the old task. And sometimes we have problems to actually pre-train them from one task to the other. Understanding how these networks store information is crucial if we want to understand these three things, these problems that neural networks have. Okay, so develop neural networks, well, we have Markov brains, we have feedback gates, and I didn't even talk about developmental encoding. Developmental encoding means that you change your encoding, your structure while you grow. Find a fitness function to evolve learning. Well, that's really an open question. That's a lot of time that I spend on this question. Figure out where memory is stored. Yes, we have a neural correlate R, which allows us to localize, to find out how information is processed. There's smearing and all the other interesting things about other neural networks and computational systems. But let's try to answer the last question maybe. Is there something that we can apply this to? And quite interesting, like 2 years ago, when I drove around Bollinger to look for the site of my new job, I ran into the following problem, or I made the following observation. I summarize this with artificial intelligence is not optimized to be nice. So I was actually in a traffic situation. And I mean, this is really difficult. It looks really difficult, the image that you see. That's from a driver's license test in New Zealand. That makes it particularly hard because it's left-sided and we struggle to find out which car drives first. But there are traffic laws, they are objectively true, and you can more or less easily train artificial neural networks with backpropagation or reinforcement learning to actually know those rules. There's no problem to train them to drive according to the rules. I mean, no problem, give or take a couple of control problems, but generally speaking, learning the rules is easy. I wasn't in that situation. I was in that situation. I just wanted to turn right in a stop street and there were cars coming, one after the other. And it turns out Sweden has lots and lots of Tesla cars. So I was thinking about self-driving cars. And I was wondering what would happen if all the cars that I'm waiting for are self-driving. They would all behave appropriately. I don't have the way of right. I have to wait, so I wait. Yeah. They would all reach their goal and I just stand there forever. And that's the moment when somebody stopped and let me in. There's a human that actually understands that, you know, this is the predicament that I was in. So following the rules or optimized or being optimized to just follow the rules doesn't mean that you're necessarily nice or conducive to work in groups. I think this is a problem that we'll face rather quickly, that if we do not train our AI systems with those unforeseeable consequences in mind, we get in big trouble. We get selfish AI that we are surrounding ourselves with. Now, the cool thing is that evolution figured out this problem quite a while ago. And there are many, many examples, but I think the coolest example that I know is hyenas and lions and zebras. Lions can hunt zebras, no problem. They're strong enough, fast enough, and a zebra cannot fight off a lion easily. Hyena, on the other hand, no, hyenas are too slow and too small, and the zebra can actually kick and kill a hyena rather easily. So hyenas cannot hunt zebras. Yeah, but still, hyenas eat zebras. And the way they do this is they wait until a lion caught a zebra. Then they come up as a pack and harass the lion until the lion says, okay, screw this, I have enough, I leave. If they would do this alone, they would be dead immediately. A lion wins against a hyena all the time. But they actually hunt as a group. They take advantage of their social environment. They can achieve more than they can achieve alone. Okay, so let's try to model that. So we have a digital hyena, that's a little triangle here. We have digital lions, that's a block. And then we have a digital zebra, that's this stripe thingy. And we have an arena where we have 4 hyenas in there. And we have 4 lions surrounding the zebra that they're eating. Now, this is a toy environment, right? Our hyenas are not really hyenas, they're agents that can turn left, right, see the environment, push stuff. Our lions actually are completely unanimated. They are just heavy blocks that make it impossible for the hyenas to actually get to the zebra. However, these blocks can be pushed when 2 hyenas decide to push at the same time. To illustrate what happens when we evolve or optimize AI to be sufficiently intelligent but not nice, we just measure the performance of these agents and run an evolutionary algorithm according to the individual performance. And what we get is, and this is the thing in the middle, and I hope it starts, yes, you see the hyenas run around. Oh, at some point they actually find the lion and the hyena. They actually manage, 2 of them, to push away a lion. That's it. 1 hyena eats. The hyena has no reason to actually go away and let another hyena feed, because it accomplishes its mission. It has to eat zebra and it only gets rewarded for eating zebra. Yes, it struggled together and found a way to push away the block, but yes, that's it. Okay, there's this concept that's called group level selection for evolution. And it's a little bit fuzzy defined, but generally speaking, when you talk about group level selection, you mean that the rewards are not distributed to the individual, but that you consider for evolutionary success, the success of the group. And in this case, we reward the hyena not by the individual success, but we reward the hyena by the success of the group. And when we evolve them, they actually manage to have more hyenas eat. But more importantly, and this is really a little bit tricky to see, I'll show you this again. You see this hyena here on the top. When we go forward, you see this hyena go to the lion and push. And it's this hyena that is eating now the zebra. I run the video again, and you just follow this hyena that comes from the top and see what it does. Okay, so hyena comes from the top, helps push, and now it actually goes away on the other side, messes around and helps another hyena to eat, simply because we applied group level selection. So evolution figured out how to do group level selection and actually create reward structures that allow them to behave appropriately and to be nice to each other. So consequently, we should actually be able to sort of apply this on other systems as well. So it turns out studying genetic algorithms, doing Neuro Evolution and so forth, also allows us to study reward structures. And if we study reward structures, we can start thinking about rewarding groups, rewarding populations, rewarding agents, rewarding robots, and so forth. One problem is that most people use reinforcement learning, and we have to actually figure out how to translate what we call fitness function to the reward function of reinforcement learning. What this cannot do is it cannot solve the hidden state problem of reinforcement learning. That's a different thing. That's something that genetic algorithms have to solve. Okay, so course summary. Contemporary AI technology is more teaching a machine something that you already know to do. It's not machine learning per se, it's really teaching machines to follow what you already figured out. It still allows for amazing advances in applications, right? I'm not saying this is useless technology, quite the contrary. It's really cool that we can do that, but it's not what I'm interested in. Well, the next step is to make machines that can learn autonomously. And we have progress in this direction. And I think it will actually mean a very, very important change in the way AI acts around us. It's actually suddenly able to act autonomously, given a particular reward structure we optimize it for. Also, evolution actually did once already figure out how learning could evolve. So instead of reverse engineering the brain and doing this, let's reverse engineer the process that actually give rise to those machines. And then two sort of fallouts from that neurocorrelates help us to understand computation and cognition, which is really important for what we do, but also for artificial neural networks. And understanding reward functions better helps us train machines better, generally speaking. Okay, thank you very much for your attention. That's the end of my talk.